Okay. So if we talk about binary operation, then we say that also what I'm going to do now is I think that the number of participants is going to be more than 99. So I have to find a way to get everyone to watch.
So he has paused screen sharing. I don't know.
Hey, are people still able to talk?
Yeah, I don't know. So no, then yeah, I'm saying
Please stop talking. Stop talking. I'm trying to do because there are more people joining and they cannot get access. So I have to solve it. Um, all right, so we go on. So we're going to talk about a binary operation, and then by definition, a binary operation is a rule. It's a rule for combining two elements to produce another element. So if we take, let's say S is a non-empty set. If we take a non-empty set S, then any function, any function, let's call this function star, such that if we take two, if we take two elements, cross S, we'll get something in X. And this is called the binary operation on S. So it's just this operation here. So we have this operation here. We take a non-empty set, then we can create a binary operation such that two elements. If we take a non-empty set S, then any two elements will act and give us another S. Of course, this this function here, this function star here, we can use several other notations. We can use notations like that, delta, gamma, this one, and so on. We can use many notations for them. Let's go on and talk about some properties of binary operation. Okay, properties of binary operations. So we say that if you take a binary operation star, if you have a binary operation star on a set S, then we say that one, the operation is closed on the subset T of S. That is, if we take A star B and we get the solution to be in T for all A, B in T. Of course, we call this closure, the closure property. 2. If we take an operation, then we say that it is associative. It is associative if we have A star B star C is equal to A star B star C. For all A, B, C in S. So this is called the associative property. Then, of course, you know a popular one as well, which says commutative. So these are properties of binary operation. Commutative, then we say A star B is equal to B star A for all A, B in S. Then 4, we have what we call the distributive property. Distributive property. So if we have two operations, are operations on a set S, Then we say that star distributes over this. If we have A star B operates C, then it will be A star B operates A star C.
Then base for ID. When I'm example.
And if we have B,
They will not base me for ID. No.
B star B operation C star A is also equal to B operation A, and then we have C operation A. So these are the four properties of the binary operation. These are the four properties of the binary operation, right? Four properties of the binary operation. So if you want to say that an operation is a binary operation, or operation is associative, then we mean that you should be able to show for associative property. You should be able to show that this holds. The property of associative holds, right? So if you also want to show that the property is commutative, a binary operation is commutative, you must be able to show for the binary operation that the commutative property holds. And then if we say that it is distributive, then you must be able to show that this property of distribution also holds. Okay. So next, let's take one or two examples. Let's take one example. Let's take one example. So let's take an example. Let's take an example where we say that. Let's take a binary operation and let these two be the binary operations. So let them be two binary operations. That are defined by. So A star B is equal to A plus B, and A delta B is equal to 4AB for all AB in R. Then the question is one, can you show that star and delta binary operations are commutative? And then two, that delta distributes, delta distributes over star, show. So solution 1. Solution 1. If we start that A star B, of course, the first thing you should ask yourself is what is the commutative property, right? So let me start with I. So I, we have commutative property. So we want to show that these two binary operations are commutative. What does it mean? It means that we want to show that A star B will give us the same result as B star A. So if we take A star B, we will get A plus B. And if we take B star A, we'll have B plus A. And since addition, right? Since addition of real numbers, so addition of real numbers, so because this addition is commutative, so it's very easy, you don't need to do much. You just, addition is commutative. 2 plus 3 is equals to 3 plus 2. So it's commutative. And the second one, so this is 1. Then the second one we need to also show is that we need to show that A operates B, A delta B is 4AB, and B delta A is 4BA. Or, what we can do in an easy way is A operates B is 4AB, but it's multiplication, so you can write is equal to 4BA. And this is the same as B operates A, this guy. So by just change of positions, we'll be able to show that. And so you can also say that, you can also draw your conclusion that this operation delta is commutative. Now, the second part, where we want to show for distributive property. So we take 3 elements, A, B, C, right, which are real. Then we check A star B, A delta B star C will be A delta. No, so let me. So delta gives us a multiplier, right? So let's use that. So let's take first A delta, then B star A. So B star A we know means B star C means B plus C. Right, and then A delta B plus C is going to give us 4A B plus C. We are just using the definitions we have stated. And this will give us 4AB plus 4AC. So if we take each of the components, 4AB, 4AC, we know what 4AB means from the definition of the delta. So 4AB means A delta B. And then we know that this is a plus. So if it is a plus, let's just write plus, right? Then 4AC will be A delta C. But we know that A plus B is the same as A star B. So here we have A delta B star A delta C. So we are just using the definitions that we have already stated. But this is not enough because this is the first part. The second part should be that the second part is that we have B star C delta A. So B star C delta A, we know also means B star C means nothing but B plus C. And then we have delta A. And B plus C delta A, we know that if we have this and a delta, then we can write it as 4B plus C of A. And then we can expand it into 4BA plus 4CA. So if you have 4CA, then you can write 4BA, right? You can write this as 4BA star 4CA. But we know what this 4BA means. It means B delta A, and 4CA means. And so we can say that delta distributes, right, distributes over star. Let's talk about the operation. Or for a binary operation, what does it mean to have an identity element? Right, identity element. Definition, identity element. if you take star to be a binary operation, on a set S, if there is an element E also in S, such that for all A in S, A operates E and gives us A, and E operates A and gives us A. Then E is the identity element. So for identity elements, it should hold two things that should hold is that if you take A in S and you take E in S, then A operates E should give us A, and E operates A should give us A. So it's not just one of them, both of them should hold. If one of them holds, the other one does not hold, then it is still not enough to say that this is an identity element. Next, I'll talk about the inverse element. So for an inverse element definition, if you take any element A in the set S, we say B set S is an inverse of A if A operates B to give us E and B operates A to give us E. So if you take two elements A and B in S, then we say that B is an inverse of A. If A operates on B and gives us an identity, right? So let me state here that where E is, right? Where E is the identity element. Of course, in most cases, we denote B, right? Or let me write, we denote the inverse, right, of A by A to the power minus 1. So let's take an example. Let's take an example here. Let's take a binary operation. Let's take a binary operation. R, R. And let the binary operation be defined by So we take A, B is equal to A plus B minus 1. Then 1, show that the operation has an identity element. And then 2, that if M is in R, then determine, right? Determine the inverse of M. With respect to the operation given. That's if it exists. So solution, let's take one. The first one, we want to show that it has an identity. For an identity, we know that if E is the identity, then A star E should be equal, A operates E should be equal to A, and E operates A should also be equal to A for all A in R. So we start and we say that A operates E should be equal to A. But A operates E, we know that A operates E here means A plus B minus 1 because of the definition we have given. And this is equal to A. So it's not B, it should be E. E. So if you follow some simple manipulations, A goes to this side, E minus 1. So this will give us E is equal to 1. But that is not enough because this is the first part, right? The second part is that now we should be able to do E operates A and get an A. E operates A means E plus A minus 1 is equal to A. So this is by definition. And again, by some manipulations, you should get E to be equal to 1. And so we conclude that because the identity in both cases is equal, then we say that the identity is 1. Is the identity. So, but you should bear in mind, if you get here, if for instance, we have in this case, E to be different from this case, then it has no identity. The identity does not exist. The second part is now to find the inverse. Of course, to find the inverse, the second part is to find the inverse. So part 2, to find the inverse, we say that we already said we have an M in R. So if we take B to be the inverse, right? If we take B to be the inverse of M, then we'll see that M operates B should give us the identity which we have found to be 1. and B operates M should give us identity which we have found to be 1. So we need to show this case and we need to show this case. And in both cases, the inverse should be the same. If it is, then it means that we have found the inverse. So how do we do that? So we start from, let me call this 1. Let me say this is 1 and this is 2, right? Of course, in the question set, I said this was I. So let's start from 1. Let's start from what we call 1 here, where we say M operates B is equal to 1, because 1 is the identity. M operates B, we know it means M plus B minus 1, which is equal to 1. And then we can say that in this case, if we take B, because we are looking for the inverse B, it means we take everything to the other side, then we have B is equal to 2 minus M. So, but this is not enough because now we need to do the second part. Also, now the second part, we must get, if we get an equal, that B is the same, then we say that then is the identity. So in the second part, we have B operates M is equal to 1. And this is B plus M minus 1 is equal to 1. And here B is equal to 2 minus M. And so we say that that's the inverse of M is, let me call it M minus to the power minus 1 is 2 minus M. That is the inverse. Of course, there are several examples as well that we can create, but the final thing I will leave you here with is a statement of fact that I call the theorem of uniqueness of the identity, right? Called the uniqueness of identity. And then the inverse element. So the identity element and the inverse element are unique. Say that if you take an operation star, be a binary operation, on a set S, then 1. If it has an identity element, then this identity element must be unique. And 2, if operation is associative if the operation is associative and you take an element from the set S which has an inverse with respect to the operation, then it must also be unique. Then it must also be unique. What does this mean? So we prove here, I prove here the first one, and then the second one, you do it yourself. So the first one, it says that if the operation has an identity, then this identity must be unique, right? So if you want to show for in such incidences, you must always consider two elements for uniqueness. We've done several examples. So that suppose that this the operation has an identity element. And also suppose that and also suppose that and also suppose that and also suppose that we have two E1, E2 identity elements. For star. Then E1 star E2 to give me an E1. Since E1 is an identity element. Also, E2 star E1 is equal to E1 since E2 is an identity element, right? And that means that E1 is equal to E2. And then we draw the conclusion that the identity element is unique. Okay. So this brings us to the end of the binary operations topic. So there are some further examples in the book that you should also try to do them on your own in the exercises as well. All right, so we'll end here today's lecture. But let me go back and we'll do a recount. We did binary operations. Then we consider the properties of binary operations. It must be a closure. It must have the closure. The closure means if you take a subset of the sets and you take elements in the subsets, then all the solutions, your operations will give you solutions in the subset. It's associative, then it must follow the associativity property. Also commutative, and then also is distributive. Then we did some examples to verify that. We did also learn about identity elements and then the inverse elements. Then we did also some examples to confirm that. And then finally, we did show that if you have a binary operation on a set, then if it has an identity, the identity is unique. And if the operation is associative and has an inverse with respect to the operation, then that inverse is also unique. That is a do-it-yourself assignment. So if you have any question,